So first, some clarifications about various just implicit definitions that I used in the last lecture. It's kind of, well, intuitive, but probably you can do a better job. First thing is, what is a random variable? Okay. And for that, we need to go back to our understanding of probability. Mathematically, yes, you can very easily define that the meaning of probability is that you have identical copies of some objects, large number of copies, and you measure some property and you will get some value, but you will get one value another time, another value another time. Find all the frequencies of how often you will observe which value and take the limit where the number of observations goes to infinity, then those frequencies will give you probabilities. That is well and good. It's not a mathematical dilemma. But physically, you will face a question: how will I make a large number of identical copies? And the answer is, it's possible, but requires putting together various ideas. If you just say that I have a picture and I will make Xerox copies, they will look almost identical, but they are not exactly identical. You will have some uncontrollable noise in such descriptions. And then, well, mathematically you wanted identical copies, physically you will say, okay, it is not perfect, but then I have to worry about how much that noise will disturb whatever deductions I make using the probability analysis. Can I get rid of the noise? And the answer is yes, but you have to put together the kind of things which I talked about in my last course, rather at the beginning of the last course. When I say I have one and another one, and that is two, counting is perfect. This finger is not identical to that. Still, how did I counted both of them as fingers? And the answer to that is digitization or discreteness. If you have discrete variables, you can assign them certain properties which are far enough so that little bit of noise does not change the value. Okay. And then it is fine. You have certain amount of noise, but the variables are farther apart. You can distinguish them even in presence of noise. And then you can assign them specific values. But this can be done with discrete variables, not with continuous variable. Continuous variable, some noise will be there, some change in the value there, you can't separate them. So it's a powerful concept, but we are so much accustomed to all the calculus and differential equations, that is how we are taught, that we don't look at that direction very much. And the reason for that is also, well, maybe some part is mathematics, but some part is our own getting used to the kind of language, that if I give an integral, say integrate x cube from x1 to x2, no problem, you write x raised to 4 divided by 4 and some limits. But if I say sum n cube from n1 to n2, it can be done, but you will have to scratch your head. What is it? Maybe it's something which is require more amount of work in the type of mathematics we use, or maybe we just learned the whole thing the wrong way. We should have learned about discrete variables and all the arithmetic or whatever linear algebra in great detail before jumping onto calculus. Part of both these features are present. And fortunately, discreteness is given to us by quantum mechanics. It's there. The fundamental particles are discrete. The fundamental properties, energy levels are discrete. And then you can talk about specific values when the noise is small enough. It's a surprising thing, but it is true. And we make use of it as well in many scientific applications. For example, you talk about a hydrogen atom. Whether it is here, whether it is another star, another galaxy, property is the same. You don't have to worry about that this hydrogen atom is little bit distorted version of that hydrogen atom, like you talk about when talking about a picture. That's not true. You can assume them to be identical, and then you can count in terms of whatever probabilities and distributions you want to construct. No problem. But this is an important point, that you have to define random variables. And random variables, you can take them to be all the variables which have some probability distribution. That is good enough. When you have deterministic values, those probability distribution will become delta function. But when you have a distribution, well, there will be some probabilities here and there, and you call them random. But the more important characteristic in dealing with random variables, you want identical copies. Otherwise, you cannot construct probabilities. The distribution may have many shapes. It may be Gaussian, it might be some square distribution, some Poisson distribution, all kind of things exist, and they all can be made use of in different senses. So that is one part needed some clarity. What do you mean by random numbers? And we use them, but I'll keep all these things at the back of your head just to avoid unnecessary confusion. And once you are convinced about that, then everything is normal. The other things which I talked about was this definition of this bounded probabilistic polynomial computation. It was rather a straightforward definition and just follows by intuition that if you add one more feature as a part of things which you can use in your algorithms or processing, well, you will not do anything worse. There is nothing more complicated than intuition, that if you add something more, as long as it does not destroy all the previous properties, it is fine. If it destroys something previous properties, then you cannot say anything more. But if it is an independent property, you add it on to whatever is there. If it is useful, you will use it. If it is not useful, you will let it be. And we did this stuff when talking about going from the classical computing, particularly the reversible computing, to quantum computing. Reversible computing was there in a discrete fashion. It was doing all the classically allowed things. You added a superposition feature to it, and it went into the quantum computing domain. Well, it can't do any worse. If you find the superposition of no consequence, don't use it. That's all. So that is a trivial way this polynomial class is extended to BPP. Now, where the boundary is in terms of what probability of success you should use, I just put a number 2/3 by hand. And that can be rigorously quantified in more detail. I just gave an argument saying that you can suppress the error rate to as much as you want, and scaling is a log over 1 over the failure rate. that many trials you need to make, but it can be made mathematically precise. I will do that when I actually work out the details in a specific example. But the fact is that you can do that using the majority rule. And why that number half appears is essentially because that is what defines the majority. Nothing more than that. If there is no probability in there which is greater than half, then I could have just tossed a coin and skipped everything else. It would have not required me to detail calculation and get a success probability of half. Okay, that is of no use. So these are concepts which are tied together, and as I said, when you work out the details, you have to add actually all the binomial coefficients when you do multiple trials, how often this possibility occurs, how often that possibility occurs, and count. But the number half will appear automatically as a borderline in that analysis. And as I said, I will go through that in more detail with specific examples. So now let me go back to the explicit construction of random walk. Okay. And as I said in the previous class, there is this heat or diffusion process, which was defined by this parabolic equation. The rate of change is proportional to the Laplacian. So now I want to construct a discrete version of this equation, because that is what we use in random walk. You toss a coin and decide I want to go this way or that way. It's a discrete process, and it becomes a very useful model. So this is discrete, and I will use one dimensional for the case of simplicity. So I have to, find discretization of both time and space. And let me start with the Laplacian. How do I define a second derivative? And that is mapped to a simple difference form. Where epsilon is some interval in space. How do I interpret this in a probabilistic language? It just says that you take the function from some location, put a little bit of it on one side and the other little bit on the other side. And if you do that, then you have a second derivative. How much you want to transfer depends on these coefficients, etc. And you can say that some part will remain wherever it is and some part I will change. Fine, you can do all those kind of things. And the largest things will occur when you make this thing go down maximum and put half on each side far away. So there is a version of an equation I can write down now by saying that phi at I have to discretize that as well. T plus delta t is transformed, or rather, well, is equal to, according to this rule, I have to put argument for space as well. So let me put both of those things together. So if I have phi of x and t plus delta t, what does it look like? So that is equal to the largest difference I will choose in this definition, that phi of x minus epsilon and t plus phi of x plus epsilon and t, and I have to put half, and that will give a discretization. What does it mean? That there was some phi at x minus epsilon, half of it went in the positive direction and landed up over here. There was some at x plus epsilon, half of it went into the negative direction and landed it up over there. Okay, that is just the maximum value where nothing remains at the same location. If you want, I can add a constant term of phi x and t over here as well, which says that some part did not move. But this is the standard construction, which says that a random walk, you start at some point, half the time you go forward and half the time you go backward. Okay, so you can now use this equation to draw a little illustration, that suppose I start at x equal to 0, and initial value is that the probability of this point is equal to 1. After delta t, what will happen? That I will put epsilon equal to 1 in this particular case, that this is 1, this is half. Half of it went this way, half of it went this way, so this is a new probability distribution. Another delta t, what will happen? Well, there was a half here, but then a quarter will go this way, quarter will go this way. You keep on juggling about various possibilities. So there is 0, minus 1, minus 2, minus 1, minus 2, etc. And now you will have a quarter, there will be a half, so this is quarter, and this is half, etc., etc. And very easy to see that what this description will produce is a binomial distribution. So this and here I put the probability half, but you can make it asymmetric also. So if I have n steps, some steps will go positive with probability p, with the other steps will go negative with probability 1 minus p, and the location will be decided by the difference of these two values, which is well, goes from n minus k, so n minus 2k, it gives a maximum negative value of minus n, maximum positive value of plus n, and goes there from one to another in steps of 2k. That's what will come out. And it's very easy to play with. You can actually calculate any expectation values with this particular probability distribution. Once you have the explicit values of all the probabilities, it is so here given by these particular values, and we know that if you directly solve this equation in the continuum, the solution is a Gaussian, and this is a discrete version of the Gaussian. If you have enough number of steps, a binomial distribution looks very similar to Gaussian, in particularly with n going to infinity. So and this is the classical version, which I call the random walk. You can calculate all the properties, whatever you want. What is the mean, what is the variance, etc. Because once you have the probability distribution, all you have to do is some simple summations, and they are all very easily calculable. Now let me generalize this to something which is called stochastic evolution. I have a certain scheme, and what it does is it allows me to go from some distribution at time t to the next distribution at time t plus delta t. But that scheme may not have to be just this binomial scheme, it can be more complicated. Okay. So what will they look like? Some notation is needed. So let me follow a convention. That phi at j no, let me call this I So this is a discretized probability distribution of this variable phi. With the probability distribution, the probability summed over all the components is 1. What it does is it starts with some probability distribution, and then some part of it is transferred to the other elements, typically the neighbors of that particular point, and that transfer process is described by this matrix Mij. How often you will transfer will depend on the values of that particular element, and it's a probability again dictated by saying that this Mij is greater than or equal to 0, and these are just standard rules, And this can be now an general matrix. It's a linear evolution buried in the fact that the equation which you are trying to map to is also a linear equation. Okay, so this is
what is the meaning of matrix being greater than or equal to 0? Mij.
You start with some probability at one particular location, and then you are going to move some population from that location to its neighbors. But that probability of movement is nothing but this particular matrix Mij, and therefore it is positive because it's a probability of movement. From this definition, immediately I can write down a constraint. So the constraint is that I was writing everything, yeah, G, okay, let this be J. That this was the old distribution, this is a new distribution. But if a new distribution is also going to be a probability distribution, it has to satisfy this. Okay. And what does this imply? Well, I put a sum on all these elements, and it just comes up with this rather simple rule. That sum of all the transfer probability along any particular row which you are dealing with, that is equal to 1. Nothing complicated. In this it is just a conservation laws. I apply it over here and this becomes then equal to 1. On the right hand side I also want it equal to 1, but there is a double sum over here. I know that this sum is over phi j summed over j is equal to 1. So whatever is here summed over I has to add up to 1 as well. This is a conservation law in some sense. And so now this is a more general matrix. Okay, it tells you that from starting from j, I will move to some neighbor I, but the sum over all the possibilities is equal to 1. And then now comes the question, what happens if I now iterate this procedure? Okay, this was just a general rule. So this has a name, and it's heavily used in computer science and statistical mechanics, which deal with this kind of transformation. It's called a Markov chain. What does Markov chain really refer to is if you are given the distribution at one time, it will give you the distribution at the next time, given by some transition rule. And the transition, so M is a transition matrix. Okay. So we can actually study some generic properties of this as well. And I mean, it is all standard stuff for those who deal with computer science and stochastic processes, but you may not have encountered it, so I will give you some simple arguments. Okay. So I can write it in a what you call matrix language, where this is a vector, this is a matrix, and this is another vector. And I repeat it means I take nth power of this matrix when I take n steps. So the question is, what will it produce when I take nth power? Okay, so it actually can be deduced on very general grounds, and that is just by using the rules of matrix multiplication, nothing complicated than that. So if I have a matrix to the power L plus 1, I can rewrite this as matrix to the power L, I, K, and nothing complicated than that, but it can now be interpreted in a different way, that this was a matrix at the previous time step. What I am doing is, I am taking the elements of this matrix and performing a weighted average. Remember, this is a matrix where summed over the first index it gives you 1. So this can be considered as a weight, which is I'm going to sum over. Okay, so this is a and this is a previous value. And I can now focus that there is a row index I and the column index is K. So what it's doing is it looking at all the elements in a single row and with various values of K and performing a weighted average. Where are the weights coming from? Weights are coming from this matrix, which is related to it, but it can be a different row, the K. So some different row gives a weight, and on this row I will just perform a weighted average. So what will happen generically, that I take a whole set of numbers and I average them according to some weight. And then I again average them at the next iteration by some weight. And I keep on averaging. Remember, all these numbers are all positive in this probability. If I repeatedly keep on averaging, it reaches what is called a fixed point or a stable result where everything becomes equal. After that, whatever weighted average you do, nothing changes because all the elements are equal. So this has a generic fixed point. Which is equal to taking this number of iteration large. So I am with n going to infinity. Just becomes a constant across the whole row. That means it doesn't depend on the column index. That's what I kept on taking the average. The dependence on the column index just drops out. All the elements become equal. And after that, the weighted average doesn't change. And this is a very general result. That you can find isolated exceptions to it, but under very general conditions, this is what will happen. Any matrix you take, as long as it has this positivity restriction, you keep on taking power of it, and it ends up being this particular matrix. And this set of Mi the so-called equilibrium or a steady state distribution. It goes towards that value and after that doesn't change. You started somewhere else, the numbers were different, but you took so many steps and all the conservation laws are present. You just reach a steady state. And afterward, the distribution is not going to change in any of this stochastic process. And that, as I said, is a very generic feature for arbitrary stochastic processes. And if you do any simulations or calculations, you will see this thing explicitly appearing. And you can see it physically also, what is going to happen. This is a diffusion equation. The particles are wandering around and afterwards it will become a uniform distribution and then there is no more diffusion. That's how the final state is reached. But this allows you to infer many things. One of them is rather trivial, that this conservation law is there. So this number should add up to 1. Whatever they are the weights. And we had this rule that, where did I write down? Mij summed over this one, j doesn't appear, so it's just rewriting that equation. And the matrix is of the form, so constant across the whole row, nothing more than that. And this structure actually allows you to do a lot of things, particularly the eigenvalue analysis. What are the eigenvalues of this matrix? Well, every time you calculate a determinant, if 2 rows are identical, determinant is 0. Okay, or when the 2 are proportional, determinant happens to be 0. And this thing is full of it. If you have, say, this matrix, I did not, n is become the number of iterations. Let me just call it n by n, capital N. So it has so I have to give some different notation. Let me call it a star for the fixed point. M star has n minus 1 eigenvalues are 0. The one eigenvalue which is left, What is it? Well, you can calculate the trace of the matrix. That eigenvalue is 1. That is the definition indirectly of the steady state. What happens when you evolve it? Well, you reached certain distribution, and then nothing more is going to happen. That is the signature of eigenvalue becoming 1. And all the other eigenvalues which went to 0 were all the transients. And they died off. It tells you more. Not only you can calculate this, but you can find this one all has gone to 0, so you will not worry about it. What are the eigenvectors of this? Okay, so eigenvalue 1 has. Now I didn't say anything about the matrix being symmetric or not. It doesn't have to be symmetric. Okay, it's a kind of lopsided structure. So you will have a so-called a left eigenvector and a right eigenvector. They don't have to be equal, but both of them can be found. So the left eigenvector, I have to put some 0 here. Yeah. What it should do is to multiply by a row vector on the left. It should give you eigenvalue equal to 1 times itself. And very easily you can write down that this eigenvector is 1 for all indices. It's a uniform constant eigenvector, because if I take 1, 1, 1, I multiply all of them with a whole set of columns, the number adds up to 1 and I get eigenvalue equal to 1. And there is a right eigenvector, which is also very easy to write down. What does the right eigenvector mean? That you take this value and multiply with that, you should get the same vector with eigenvalue 1. Okay, and that just happens. What happens if I multiply with all of these numbers with some numbers over here, and the answer is just this. It is the equilibrium distribution given by these values of mk. Nothing complicated. You just have to see that if I take this number, whatever it is, multiply by the whole row, all the values here are constant, so they just add up to 1, and I will just reconstruct the whole whatever value I had, nothing more than that for any row. And so this is in fact telling you much more, that it tells you what the equilibrium distribution is going to be as well. These are the same numbers. They are becoming the population also, because population defines the eigenvectors. But now I can go back. That is an interesting result, that I know that m star is the asymptotic limit with large number of steps, what can I say about M? So the eigenvalues what it has to satisfy that if I take a large power of this matrix, the eigenvalue is either 1 or 0. And so for the individual matrix, it will be a root of that power of the value 1 and 0. Okay. And well, taking roots of 1 and 0 is not complicated at all. 0, there is no problem whatsoever, but 1 can have many roots. And at least and the answer after a little bit of thinking is that you have to have one eigenvalue equal to 1, because that is the only one which you take a large power will produce 1. And everything else has to be connected to 0. They can be any number less than 1. And these are all the transients. This all will have eigenvalues less than 1. And you can say more things about it, but what is mostly important is the something called the spectral gap. Is defined as the largest eigenvalue minus the, I have to use some symbol, okay, lambda. The smallest difference from 1, which is the largest value of the eigenvalue among the transients. So that is called a spectral gap. It governs how fast you will approach equilibrium. The largest among this is the one which will go to 0 the slowest. So it is the most important non-trivial mode, and it will go to equilibrium, but it has the slowest decay in some sense. And this one is equilibrium, nothing happens to it, it remains steady, and that allows you to identify which one of these transient is important. And most of the time, knowing this is kind of enough, because you are interested in not only just equilibrium, but if you perturb it a little bit, how fast you will come back. Okay. So that is basically dictated by this spectral gap. And the other feature which is kind of dictated by this property, so this all transient eigenvectors have Important fact, they have negative components. Why? Because they have to be orthogonal to these objects. Remember, this is not a Hermitian matrix, etc. The orthogonality is not the same, but there is still a version of orthogonality which survives, which is you can see that if I take what you call dot product of this with itself, it doesn't give me something meaningful. Just by this itself, it will get m square, and sum of m square, what it is, I don't know. But the dot product of this is equal to 1. Okay. So the orthogonality or orthonormality holds between left eigenvectors and the right eigenvectors. Not within the individual sets, but one on the left side and one on the right side. So you can take EL, P and dotted with can form a relation like this. Okay. And that is enough to deduce that when I take different eigenvectors, P is not equal to Q, I must get this dot product equal to 0. All the elements here are positive, and the only way I can get 0 is whatever is the other component, it has some negative entries. And that is a funny feature of these transients. It's a disturbance on top of the equilibrium distribution, but something will go up, something else has to come down. Can't have it any other way. And well, you can think about it a little more, that these eigenvectors, because they have negative components, you can't call them distributions. It doesn't make sense of having some number like this, because it's not that. It's a perturbation. And perturbation can have something positive, something negative, and the sum of the whole thing is equal to 0. Okay, so this is whatever this transient eigenvectors are, you interpret them as some kind of perturbations. So this is the generic story which you can deduce without doing too much algebra. It's a very straightforward logic. You just have to think in terms of matrices and their behavior with the important constraint of this conservation law. And then everything just comes out, doesn't depend on specific details of the problem at all. But there is one crucial property which is buried inside it, that any process which will have this kind of steady state and equilibrium distribution has limitations about going backward in time. Okay. You approach the equilibrium, but where did you come from? That memory is lost. That is a typical situation in any of this diffusion equation, because it's an important component of dissipation. So, how do I see it in this matrix language? Well, I can ask, if I interpret that as matrix equation, I can define the inverse process by calculating M inverse. I can design a matrix where the inverse is defined. It's not too complicated. But now try to understand what happens if I try to evolve this scenario backward in time using this M inverse. We saw these properties of the eigenvalues. Eigenvalues of M inverse are reciprocal of this. Nothing complicated, it doesn't matter what type of matrix it is. You can just take the eigenvalue equation and multiply by M inverse. So one of the eigenvalue. That means the M inverse has one eigenvalue equal to 1 and all the other eigenvalues are greater than 1. Okay. What does it mean that you tried this? The steady state part will survive, but all the transients are going to grow. That's what it is designed to do anyway. So some of these elements, in whichever way you want, phi I are going to increase. Some combination, doesn't matter, whatever it is. But that runs into trouble, that the sum of the values still has to be equal to 1. And they are going to grow, at some point they will hit the boundary. And well, the sum will remain 1 by construction with the matrix, but it will then land up in trouble with this assumption. The sum can be 1, but all the individual components cannot remain positive. Some of them will turn negative. So, when sum phi I is it breaks down the assumption about the probabilistic distribution you made. You can go backward in time up to some time. Further going back in time is not allowed. There is no meaning to the stochastic evolution for arbitrary past history. And that is the nature of the dissipative process. In a very general scenario, something is always going to get lost. You cannot try to reconstruct, and if you force it, then the violation of some of the axioms will, or initial definition will appear. So this is quite a general story about the whole stochastic evolution framework, and in particular, what is this Markov chain. All the analysis of statistical distributions, what will happen under very general scenario where you have some transition elements between values at one time and the values at next time. And a lot of computer codes are also written in that particular fashion for stochastic processes, because that is what you do. One clock cycle to execute this iteration, next clock cycle you execute another iteration, etc., and you continue this process. In problems which have some significance, you hope to reach the steady state by doing whatever it is, and then you can extract some meaning from the answer. If you can't do it, then well, you have to find some other way of tackling the problem. So this is all the so-called classical business of evolving according to some probability distribution and interpreting this equation as a diffusion process. But this scenario needs modification when going to quantum theory. And as I mentioned last time, the difference from the Schrodinger equation was just there was an I sitting over here. Nothing more complicated than that. But on the other hand, we also know that Schrodinger equation is not a diffusion equation, it's a wave equation. So how does that modification enter this particular whole analysis? And that enters at a very fundamental level itself, that I can write down this kind of evolution, but this matrix is going to be a unitary matrix. Okay, it doesn't have these properties, it's something else. And that fact drastically changes everything. So, well, I can give you an example first and then give more detailed explanation later. So this is a unitary evolution. Unitary evolution will mean that all the eigenvalues are of absolute magnitude 1. They are all just the phases. So this stuff is not going to be there. Or rather, there will be one eigenvalue still equal to 1, but the other eigenvalue have different phases, not different magnitudes. And so they are not going to decay. And that changes, so whole picture. There are not going to be transients and some equilibrium configuration or anything of that particular type, the inverse always exists. So backward evolution is not going to run into any problem whatsoever. And so what does it produce? So these are the kind of generic thing, but instead of trying to take this differential equation and construct what can be called a quantum walk, let me work the other way around. I will take a quantum walk basically defined by some matrix, which is a unitary matrix, and try to find out what its properties are. Okay. So again, one-dimensional situation, and I will take the simple-minded example like this, where you are at some point, you move left towards the point with some probability, right towards some probability, and these probabilities are not going to be replaced by some matrix elements of the unitary matrix, but it is fine, and see what happens. So let me write a simpler situation, which is our translation this is again local. So I go from a point to only its neighbors, and translation invariant means that these probabilities which I am using, they are the same at every point. So if I'm here half the time, I will go there, and half the time I will go there. Doesn't matter at which location the probabilities are different. So I will write a matrix. So this is U, and I will give it a little more freedom. So I will write 3 elements, B, C, and A. And this stuff is 0 and 0. Okay. What does this represent? That if I am at some location with amplitude B, I will remain where they are. Amplitude A, I go left. Amplitude C, I go right. Okay. It just mimic whatever is happening in this other random walk case. But now I have to satisfy the unitary constraint. And that means that these rows have to be normalized. So one of them is this mod square norm is 1 of any row or any column. That is not a problem. Other thing is orthogonality. So now I take the product. Okay. So what is the product of this with this? I have to complex conjugate one of them. So B times A star plus C times B star is equal to 0. And the other one is simpler. So dot product of this times something which is 2 steps away. So that will give C and this turns out to be the most stringent constraint. tells you that either C is 0 or A is 0. And now one can work backwards. Suppose C is 0. Then this term disappears. Then this will tell either B is 0 or A is 0. So whatever combination you try, you'll find that two of them are 0. Okay. So this will also tell you that another one is 0. That is what.
Isn't the B always 0? Isn't the B always 0? Say C is 0. Then that one says.
I can make both A and C equal to 0. This will be satisfied and B will remain non-zero.
Oh.
That is a trivial case. So it just says don't move. Wherever you are, just stay put. So it's a very peculiar situation. So it's either stay put or monotonically move in one direction.
Can you explain why translation very important?
Hmm?
Why did you consider the translation?
So I wrote all the rows to be the same. The transition matrix is independent of the location. So what does this mean? If you say this is one of them is you started here, you just keep on moving in one direction or you keep on moving in other direction. And if you think about it a little bit, this is what a wave does. Monotonically moves in one given direction. You started at some point, it will create a wavefront and it will keep on going. It is not going to go back and forth. Of course, this stay put means you make this thing very heavy and it's not going to move at all. That is a kind of trivial situation, but this is the wave motion. Constant speed. And its magnitude is also fixed because two of them, if you take to be 0, then the first one will take the speed is 1. That is the wave speed. So yes, you started with just writing a general walk description, it came out by putting this unitary stuff inside it. And it's a straightforward enough consequence, but there's a lot of it buried inside the detailed analysis which one can do. Where does various ingredients are buried, illustration is enough that yes, something is different and you have to take care of it. But what is the more general situation that occurs? And then you think about little bit more about how you would try to create this random process. Okay, so in that classical language, you said I am at this position, I will toss a coin, half the time I go there, half the time I go to the other side. Can I do with the unitary matrix that kind of toss up? Well, I need to consider superposition of a coin and then a control not operation. Okay. Studied if say the state is 0 plus 1 by root 2, I can construct it and then it controls something else. It just says if 0 do this, if 1 do something else, you can do it. So I can write down the operation. So let's see what happens. So I am say in the state X and I put the coin in this particular state. Okay. And then I will define a control, well, not control not, but some related control operations which says that if 0, then take x to x minus 1. If 1, take to x plus 1. Okay, so this is and you can construct it. It's not complicated. You can perform some transformation or this you can construct explicit circuit. But now see what happens. That it will give the 1 by root 2 is there. It will produce a state like this. But what has changed? These are two different factors. This one cannot be factorized. It's entangled state. If you put some simple label, you can make it look like a Bell state. So the coin is no longer independent of the dynamics of the object which is making the walk. Coin is entangled with it. It's not independent of degree of freedom, where in classical cases, first step I will just toss one coin, do something. Second case, I will again toss the coin, do something. There the coin had no relation with the actual transformation of the system. Here the coin is entangled. I cannot throw it out. Saying I tossed the coin, I used it and I can't throw it out because it is entangled. It's part of the whole dynamics for anything going more. And that is so coin cannot be discarded. I have to keep track of the coin throughout. So this is a feature brought in by the unitarity of the dynamics in a certain sense. That coin is not an extra degree of freedom, it is part of the dynamics. The motivation for doing all the randomized algorithm is giving an extra degree of freedom to enhance the capability of the algorithms, where here it's not going to remain an extra degree of freedom, it's part of the whole story. You just have to include it or equivalently work in a larger Hilbert space, which includes the coin. And yes, there's another feature which says that some things are going to be different in the quantum case. And one can work out more detail. My time is getting over. One can work out more details, but I can give you the answer that I can now work backwards. Well, two things I can mention, but that is fine. One of them is I take this structure or this unitary matrix and convert the discrete language to differential equation. What will I get? I must get a wave equation, but it already told me a lot of these properties, that it describes a wave moving at a constant speed. And that occurs relativistic quantum mechanics. It's a feature of relativity which says that wave is moving at a constant speed. It's buried inside this thing in simple manner, but I will do that, show you how this whole analysis ties up with that. But it has to come out. The properties are already there. And then you ask, what is coin? It's a 2 degree of freedom which are buried inside it. It's part of the Hilbert space. And what will be its analogous label in relativistic dynamics? It's a label between particle and antiparticle. They are always there. As long as you put in relativity, energy will come with a square root. In the standard dispersion relation, E is equal to square root of p square plus m square, the plus sign and a negative sign, and then you identify those plus and minus as particle and antiparticle modes. They automatically come out, doesn't matter what the other details of the system are. As long as you put in relativity, this is and the coin maps to particle-antiparticle transformation. There are lots of features between particle and antiparticle. I don't know whether you have studied any of these quantum versions in the relativistic language, but it's equivalent to going backward in time. So particle goes forward and antiparticle goes backward. It kind of connected with the standard evolution. You write e raised to I et. So energy changes sign is equivalent to changing the sign of time. Keep energy positive, one of them will go forward, the other will go backward. So there are lots of interpretations like this, but this is what will emerge if you now try to make this thing mathematically complete for generic situation, not just a particular case. So this is one interesting point. And there is another interesting point I can make in relation to this stochastic dynamics, because it also appears in many places. So question is, I have this matrix and this population business. Can I retain some of these properties and still include some part of the unitarity? So it's possible that this M together with keeping this conservation law, but giving up positivity. Okay. And if you work it out, both the constraint that this says all of this is satisfied, and unitary just means that M dagger M equal to identity. Can you solve these equations? And the answer is yes. And the answer turns out to be unique in case of this translation invariant system. And that answer is nothing but Grover's diffusion It's called a diffusion matrix because it simultaneously satisfies both these properties. And if you remember, it had entries like that all the off-diagonal elements were 2 over n, and the diagonal one had a -1 added to it. And it satisfies this property because you add up, there are 2 over n times n, which will give 2, and it will add up to 1 with a -1 in it. And if you square and check all the orthogonality, it works. Because it was designed to be an orthogonal matrix to begin with, a reflection operator. what it doesn't satisfy is these numbers minus 1 plus 2 by n is going to become negative. And surprisingly, it is a kind of unique answer, both satisfying the diffusion constraint and the unitarity constraint. And we will find this thing useful in some algorithms for that reason.
From here, we obtained this summation in J Mij equal to summation in J Mij equal to 1. From here, we obtained
That was this condition which I was writing. No, I somewhere not over J, but I was writing. This condition, the conservation law. Here it is a symmetric matrix, so it doesn't matter, but this was to satisfy that if the initial normalization is present, the final normalization should also be preserved. So that gives this particular constraint, and it's true for Grover's matrix as well. But you can choose these numbers to be positive, the eigenvectors, elements, whatever they are, but some of the entries of this matrix are going to go negative. So I just illustrated this for the purpose of emphasizing that there are no quantum features. Next time I will derive this consequence just on the fundamental grounds. What is going to come out from what is called a quantum walk, and deliberately the word random is omitted. That is because it's going to not do a random stuff at all. It's a wave dynamics. It's better to not confuse it with going things back and forth. And this is a big subject in itself. If you want to look up, there are papers, or basically a good review article, if I have the number here. The article has too many things, so it may not be useful in a great detail, but if you want to study it, the subject is big enough, so it will take a whole course on itself if you want to do it. But this is a paper on archive. It's a review or introduction, whatever you want to call it. You can have a look.
if we go backwards in time, so are you saying that y itself is at
No, whatever operation you have, the inverse operation exists. So you can apply the inverse transformation to go from an entangled state to a factorized state. There is nothing which is forbidden. When you created Bell state from initial state, it was like zeros and ones. And you can apply the other way around also to go backwards. The rules of quantum mechanics do not forbid it.
how this is related to particle and antiparticle?
That's what I have to explain next time. It's not going to get factorized, it has to become part of the Hilbert space. And you have to find an explanation or interpretation of what that extra degree of freedom is.